In this video, I want to introduce the notion of the gradient of a function of two variables. So if we're given a function, f(x,y), that actually has partial derivatives, fx and fy, then we define the gradient as follows. The notation is this upside down capital delta. It's sometimes called del. So I just call it grad or gradient, just gradient of f is equal to this vector that in the first position has the partial of f with respect to x, and in the second position has the partial of f with respect to y. This is usually the way it's written. Sometimes, though, you'll see it written with a little vector hat put on top of the gradient, just to emphasize the fact that the gradient is a vector, right? The output of the function f is just a single variable, just a single number. For each input, you get a number out. However, the gradient of that function is a vector. A function of two variables, this is a vector with two components. Now, what does this gradient do for us? Well, I'm glad you asked. It does stuff for us algebraically and geometrically. Algebraically, it simplifies some expressions and ties some things together. For instance, the chain rule, right? Given a function of two variables and a vector function, r of t is x of t comma y of t, you can think of the output z as a function of t because you can calculate r of t and then you take the x and the y from that and plug it into f anyway. So you have z of t is f of r of t. And then you could say, well, what's the derivative of that with respect to t? So dz dt is, and this was the chain rule that we had, take the partial with respect to x, then multiply by dx dt, take the partial with respect to y, multiply by dy dt, and add those two things together. Which we could, if we wanted, I don't think we did this yet, but we could write this as a dot product. Take these two, write them in one vector, take dx dt and dy dt, write them in the other vector here, and we have this dot product. This first vector is what we're calling the gradient of f. And the second vector here, dx dt, dy dt, is just the derivative of r. So this is r prime of t here. Which, replacing that x comma y with r of t, what I see is that the derivative of f of r of t is the gradient of f, leaving r alone, dotted with the derivative of r. This looks a lot like the old chain rule from Calc 1, right? The derivative of f of g of x is the derivative of f of x, leaving g alone, times the derivative of g of x, right? So you derivative of the outside function, leaving the inside alone, times the derivative of the inside function. Now, it's not the derivative of the outside function, it's the gradient of the outside function, leaving the inside alone, and then dotting with the derivative of the inside. Okay, so the gradient here is really playing the role of that the derivative played in Calc 1. So simplifies expressions and plays the role of the derivative. How about the directional derivative? I think we looked at this in the last video a little bit. The directional derivative was, by definition, if I'm given a function f of xy and a unit vector, a comma b, then the directional derivative in the direction of u is the partial derivative of f with respect to x times a, the first component of u, plus the partial derivative of f with respect to y times b, which is the y component of the unit vector. Right? We can, and I think we did in the last video, write this as a dot product. The fx and the fy get put here, that's the gradient, and dotted with the unit vector. So the directional derivative is the gradient dotted with the unit vector. Right? This is particularly nice. This is going to give us a lot of the geometric significance now. So the geometric significance of what the gradient is going to do for us. And it gives us all the information about the slope that we want at a point, right? That is through this gradient dotted with u. You tell me what direction you want. I can tell you the slope in that direction because I just dot whatever direction you gave me with the gradient, and that'll be the slope in that direction. It also tells us the direction of the largest slope, which we'll see below. It tells us the magnitude of the largest slope, which we'll see below, and it gives us a vector perpendicular to a level curve, which is really the topic of the next video. But let's talk about these geometric significances here and how that all comes into play. The directional derivative is given here. That was what we just showed right there. Now, but this dot product can be written as, as any dot product, the length of one vector times the length of the other times the cosine of the angle in between them. Now, u is a unit vector, so the length of u is just 1, right? So this is the length of the gradient times the cosine of the angle in between the gradient and the direction that you want the directional derivative in, right? Couple of things to notice. That the cosine goes between -1 and +1, and its maximum at +1, and that happens at theta equals 0, or theta equals 2 pi, right? So when the angle between the unit vector and the gradient is 0, that is, they're pointing in the same direction, then you get the maximum directional derivative. The slope is steepest in the direction of the gradient. Right? When say one of the things I think about what the gradient is good for. It actually is showing you. Well, here it's showing. We just showed showing you the direction of steepest increase, which means if the gradient is pointing this way, then minus the gradient is the direction of steepest decrease. That would be when theta is pi and cosine of pi is -1. So the greatest decrease would be that way. And if you're thinking of your surface as maybe terrain, land, and it rains. When the rain hits the ground, what direction does it flow? Well, it's going to flow in exactly the direction of downhill as fast as possible, which would be minus the direction of the gradient. Also notice that in that direction of steepest increase, right, the greatest slope in the direction of the gradient, cosine is 1, that the directional derivative in that direction is actually the length of the gradient. So the gradient is pointing in the direction of steepest increase, and its length is the slope in that direction. Now, I want to point out that when I was learning this, I had one misconception that took a long time to get over in getting that gradient to do what I thought it should do. Right? Because I pictured the gradient pointing up the slope. That's how I had a picture in my head of what the gradient vector was doing. That you find the direction of greatest and it's pointing up the slope. But it isn't. Right? This gradient, this function of two variables, f, when you take the gradient, it's a vector with two components. It doesn't have a z component. It's just telling you in the xy direction, look that way, and the ground will be going up as steep as possible. Right? If you looked some other way, you wouldn't be going up as steep as possible, or you might be going down, whatever. But in the direction of the gradient, the surface will be going up as fast as possible. That is the greatest slope. But it doesn't point up the slope. It points whatever. If you got this thing going this way, the gradient points into the hill, right? Because the gradient tells you the direction to go uphill. So in this example that we had in the previous video, if you take a look at it in 3D, let's see, I'll move my face again here so that I can get the slider. I have down here the gradient plotted in now, and this vector is the direction we're looking, and so that curve up here is always over top this thing, and as I slide this around, you can see that the curve changes, and it's hard to tell exactly what, because you can look at this from so many angles, what is uphill and what is downhill, but positive z-axis is going here. And the question is, when are you going up as fast as possible? And the claim is you're going up as fast as possible when you're looking in the direction of the gradient. So that would be about right here. So that's headed right up towards the top of the hill there, right? The gradient. is the direction of steepest increase. The length of the gradient is the slope in that direction. Now, let's actually do an example here and do some calculating. Here's a function, x squared minus y squared over 5. The over 5 is just because when I draw the graph without the over 5, it's really tall, and so this just scales it down to a manageable picture here. So this is a hyperbolic paraboloid. Right? The gradient is a vector. I will say that many times because you've got to remember that it's a vector. Partial with respect to x is 2x over 5, and partial with respect to y is minus 2y over 5. Just as a for instance, here's the point 1, 2. The gradient would be 2/5 minus 4/5. Notice this is not a unit vector. It's a vector that points in the direction of steepest increase, and the maximum slope at the point 1, 2 is the length of this thing. It's 2 over the square root of 5. So here it is in a movable form. Again, the gradient I have drawn in. This is the point 1, 2 in the xy plane. When you plot it on the surface, it's down here. This is the gradient, so it says if I look in that direction, I should be going up as steeply as possible. All right. And so looking in that direction, and that's headed up as steep as it can from that point. Again, it's tricky to see with these. Because I can make it look like, oh, it's going this way would be the steepest, but the z-axis is pointing kind of towards me here. That's the direction of steepest increase, and the slope in that direction, I think we calculated, was 2 over the square root of 5. So there's a brief introduction to the gradient. In the next video, we will do some more work with the gradient and show how the gradient is connected to level curves.